Okay, now that we've learned a bit about the different kinds, or some of the different kinds of mountains, definitely that's not an exhaustive list of mountains, but now that we've talked about some of the kinds of mountains on Earth, we're going to talk a little bit about how the continental crust behaves. And one of the important things about continental crust, and in fact any crust we need to think of, is isostasy. And isostasy is defined as the state of gravitational equilibrium between Earth's crust and mantle, or you can say the Earth's crust being in gravitational balance is also sometimes used. So the crust basically floats at an elevation that depends on how thick the crust is and how dense the crust is, basically kind of how heavy as it is. And it's really kind of like thinking of how an ice cube floats in water, or how if you had a wooden block sitting in water, how it would behave. So let's say we had a wooden block floating in water, and we add some weight to that wooden block. Well, what's going to happen? It's going to sink a little lower in the water. If we remove that weight, it's going to rise up a little higher in the water. Crust behaves the same way. Crust, if weight is added, will sink a little. If weight is removed, will rise a little. So this is isostatic adjustment. This is the process of establishing a new level of equilibrium. So I always like to say, picture a ship being loaded and unloaded, right? As you load cargo into a ship and weight is added, it's going to sink a little bit lower in the water, and then when it gets where it's going and they unload the cargo, it's going to rise a little bit higher in the water. And crust, like I said, exactly the same. But when we think of weight being added to the crust, we're not adding cargo or adding something like that. It's any kind of weight, like thicker crust, like a big mountain, right? A big mountain's going to weigh a lot because there's a lot of rock there. Or if we add a glacier, that might be 3-4 kilometers thick of ice. That's going to weigh a lot. And so if we add this weight, the crust is going to sink a little bit deeper into the earth. And underneath mountains, there's something called a root. So if you look at ice cubes in your drink next time, you're going to see a certain amount of the ice cube is above the water line, and then there's a certain amount that's below the water line. That part of the ice that's below the water line, that's like the mountain root. That's the part of the mountain hidden from us. So if we have a big tall mountain like this, and we think of our wooden blocks, right? There's our water line. When the crust is thicker, there's more of a root hidden underneath. And the same goes for mountains. If we have a thicker mountain here, we're going to have a thicker mountain root there. And then what will occur is if we start eroding this mountain and reducing the weight that's there, this will all start rising. That's this isostatic adjustment. If the weight is removed, erode the mountain or melt the ice or take away whatever extra weight is on the crust, then things will rise. The root will rise. And ultimately, through weathering and erosion and this adjustment, this rising of the mountain root, this is how we can expose rocks that form deep, deep underground, those metamorphic rocks that form many kilometers underground, or those intrusive igneous rocks that form deep underground. Those get exposed because of this erosion and uplift and this isostatic adjustment that occurs. And so you'll see rocks like this that originally were deep underground. You can stand on them today because the mountains eroded away and these were uplifted. I've talked about glacial ice causing this as well. And so during the last glacial maximum, large parts of North America and Europe and a few other places were covered by really massive amounts of ice, sometimes 3 to 5 kilometers thick. And so that ice weighed down those areas because really every gallon of water weighs something like a bit over 8 pounds. And if you have 3 to 5 kilometers thick of ice, Well, that's going to be a whole lot more than just 8 pounds. It's going to be a lot of weight. And that pushed down the crust. Now, with all that ice gone, the crust is adjusting itself to having lost all that weight. And as the crust adjusts itself, as it rebounds from that weight of the glacial ice, you can actually have earthquakes occur as a result of this. So in any case, this is looking at the last major time we had ice covering much of North America during the last ice age. So ice covering all this area. And if we look here, this is showing uplift rates, where the greatest amount of uplift is kind of in your red colors and the least is in the blue. So where we had the most amount of ice, that's where we're having the greatest amount of uplift because of that isostatic adjustment. So just remember, the major rule to isostasy is that you add weight to the crust, it's going to sink a little bit, and you take away weight and it's going to rise. Doesn't matter what that weight is, whether it's ice or a mountain range, but as long as you're adding weight, you're going to push the crust downwards. You remove weight, you're going to make it rise. Now, the last things I want to talk about is something called continental accretion. This is how our continents have changed over time. The initial continents that we had way back billions of years ago in Earth history were actually quite small compared to what we have today. So they began as these like little small pieces of crust, and today we have what's known as the shield that exists in all continents. And the shield is kind of that old original core, the original part of the continents. And the rocks are always older than 570 million years old, in many cases much, much older than that. And in fact, in these shields, we can find some of the oldest rocks on Earth because the shield is that old original part of the continent. So every continent has one of those. You can see in Europe it's the Baltic shield, and South America it's the Brazilian shield. Here in North America it's the Canadian shield because most of it is located in Canada. And there you can see some of the rocks of the Canadian shield. They do extend downwards here into some parts of the United States, but like I said, most of it's concentrated in Canada. And if you're flying over the Canadian shield, that's pretty much what it looks like. If you're on the ground, it looks kind of like that. Now, in addition to having the shield, you have the basement part of the continent. The basement, when we talk about the basement of the continent, it's basically the foundation of the continent on which all other rocks are piled up. So the basement's going to be these old, intrusive, igneous, and metamorphic rocks. And then younger sedimentary rocks might be deposited on those. An interesting fact about the basement rocks is they get progressively younger from the original shield. So we have the original old core of the continent, and then as we work our way outwards from that old core, the basement kind of starts getting younger and younger and younger and younger. Now, this might differ a little bit from the shield because in the shield, those old original rocks are exposed at Earth's surface. And in much of the basement rocks, other than the shield, these rocks are covered by those younger sediments, like what we see in the Grand Canyon. Down here, this is called the Vishnu schist. That's an old metamorphic rock. And then all of these are younger sediments piled on top of that old metamorphic rock down in the Grand Canyon. We also use a term when looking at continents called the craton. The craton is the stable part of the continent. And what we mean by stable, this is an area that has not been affected by a mountain building event in a long, long time. Okay, so it's going to include the shield and much of the basement. No mountain building or other tectonics have taken place there for the past, say, around 570 or so million years. So in North America, this whole area is the craton. That's that stable area. No mountain building for quite some time. And then we have the deformation around there from much younger mountain building events. Now, how come that core, the original part of the continent, that shield, is in the central part and it gets younger, the basement gets younger as we spread outwards? Well, in order to understand why we see that pattern, we have to look a little bit at terrains. A terrain is a small crustal block, so it's a piece of crust that has geology that's completely different from stuff that's surrounding it. So it kind of has its own geologic history. Some examples of terrains are things like microcontinents, like Madagascar. It's a piece of continental crust, but it's not an actual, like, entire giant continent. Island arcs, like Japan, those also count as terrains. Again, they have their own geologic history, unique from things surrounding them. Volcanic islands like Hawaii. Well, Japan is a volcanic island. What makes these different? This is created in a subduction zone. This is created by a mantle plume. But a volcanic island like Hawaii or like the Galapagos Islands or things like that, they count as terrains. And then ocean plateaus. There's an ocean plateau called Antang Java. And these are areas of extra thick ocean crust. Those also count as terrains. And what all of these terrains have in common is they are either too thick or too buoyant to be able to subduct. They're unsubductible. All right, so terrains, too thick, too buoyant to subduct. So when these terrains end up colliding with the continent, so imagine we have a subduction zone coming along, and there's a terrain sitting there. It gets carried to the continent and slams up against the continent. It's too thick or too buoyant to subduct, so it gets added to the continent. It gets sutured on there. So these subduction zones are kind of like conveyor belts that carry these terrains to the edge of the continent and then adds it to the edge of the continent. And this is how continents grow over time. Right? These continents grow as these terrains get added, and that accounts for the ages that we see. So we have our original old core of the continent, right? We have our shield, and then it gets younger and younger and younger and younger because, you know, this got added, and then this got added, and then this got added over and over, slowly growing the continent to what we see today. Now when we look at these oldest rocks, because that's kind of neat, these oldest rocks are a way for us to peer into the long distant history of our planet. The oldest rocks that are absolutely positively, we know this for a fact, are the Acosta gneiss, that are dated to just over 4 billion years old. And those are off in Canada. Now, there might be some rocks that are older than that, but these are the focus of an ongoing study, so we're not positive yet. We think the Nuvuagetuk greenstone is as old as 4.28 billion years old. But like I said, that's not for sure yet. Ask me again in a couple of years and I'll see if we know for sure at that point in time. Now those are the oldest actual rocks, right? Rocks that you can pick up and hold. The oldest mineral grain, so like the oldest little grain of sand or individual mineral that you have, was found off in the Jack Hills in Australia. And it is a piece of zircon. And zircon is a very resistant mineral. It can survive for a long time. And the oldest one has been dated to 4.394 billion years old. Now the rock itself is not that old, but this thing is inside it, right? It's in inclusion, so it's older. The rock's only 3.1 billion years old, but that little mineral grain is the oldest thing that we know of here in the continents on Earth. This is the Acosta gneiss. So that's that 4.03 billion year old rock up in the Northwest Territories in Canada. And that's the Nuvuagita greenstone. And it's off in Hudson Bay, a locality, I think it's called actually Porpoise Bay. But those might just be the oldest rocks on Earth. And this is what a zircon looks like. And so those are those very resistant to weathering and erosion minerals. And so they can survive for a long time on Earth. And that's the oldest thing we have is an individual zircon grain. And this is just showing you some of the old areas, the oldest parts of the planet. That's this Archean terrains. Those are some of the oldest areas. And these are showing some of the dates that are gotten from those very, very old rocks on Earth. And that brings me to the random picture of the day. I just think this is kind of fun because this is where my family lives. This is where my husband's family comes from. Granted, he likes to point out my family lives in the nostril. So, oh well. Anyway, that's it for mountains and continental crust. See you next time.